My name is Charles Henderson, and I am your MC this evening. I am a professor in the Department of Earth, Energy, and Environment at the University of Calgary and have been teaching here for 35 years. It is wonderful to have so many people join us in person and online. I understand we've had up to 400 registrations for this evening's EARTHx talk featuring Dr. Nathalie Nguyen-Quoc Ouellette. This year's EARTHx series has been generously supported by the Gallagher family. We've organized tonight's event as a hybrid event so that we can continue to engage with attendees from around the world and also to welcome audience members to our campus. Whether you are here in person or joining us online, we're glad you have decided to spend some of your snowy evening with us. I would like to mention that tonight's question and answer session will include questions from our online and in-person audience members. Our mic and speaker system will give our online guests the ability to hear questions from our in-person audience. If you are joining us online, you can text us with your questions. Not yet. You can text us with your questions to 403-708-5749. And don't worry, we'll show you that number on the screen as we get closer to the question period. We are situated adjacent to the Bow River, which has shaped this land and its people throughout the Holocene epoch. Many of us are fortunate to call this beautiful and peaceful region our home. As we begin this evening's session, I'd like to take a moment to acknowledge that we live, work, and learn here on the traditional territories of the people of the Treaty 7 region. They include the Blackfoot Confederacy, composed of the Siksika, Piikani, and Kainai First Nations, as well as the Tsuut'ina First Nation and Stoney Nakoda, including the Chiniki, Bearspaw, and Goodstoney First Nations. The City of Calgary is also home to Métis Nation of Alberta Districts 5 and 6. Since 2015, this department has had the privilege of organizing the Gallagher Colloquium lecture series, now known as EARTHx. These presentations allow our department and the Faculty of Science to welcome and host world-class researchers who share a passion for science, scientific research, and exploration. I'd like to take a moment and recognize the Gallagher family for making this series possible. The Gallaghers are long-standing champions of access to earth science for everyone. Their support allows us to promote and build public awareness for science and scientific research and helps people understand why science is fundamental and important not only to our own lives, but to the world that we all share. We are grateful to be able to host this important lecture series. I'd now like to welcome Dr. Kristen Bates, the Dean of the Faculty of Science, on stage now to say a few words about our department in this event.
All right, well, thank you, Charles. So, as most of you know, I'm Kristen Bates. I'm the Dean of the Faculty of Science, and unlike Charles, 30 years, I've been here for 2 years. But I love it. And tonight, we have an amazing opportunity to journey outward from our home on Earth and look towards the distant skies and beyond. The EARTHx series is all about understanding our planet and the places in the universe, from geological forces to cosmic ones. And it takes collaborative teams of scientists to answer these questions. Our Department of Earth Energy and the Environment is the first of its kind in Canada to take a transdisciplinary approach to key challenges, issues like water security, energy security, and natural hazards, the planet's past and the future of our planet. But we don't just do amazing work on Earth. This is the greatest secret of the University of Calgary. We are also Canada's leading space university. We have, here in the Department of Physics and Astronomy, we are the leader in Canadian Space Agency funding for all of Canada, as well as we have the most amount of NASA funding outside of the United States. I cannot underemphasize how important this truly is. We are Canada's space university. Over the next year, this will no longer be a secret if my team does its job well. And we're going to do it well. And our space researchers are achieving some remarkable things, from mapping the cosmos to unlocking the mysteries of our galaxy. They are developing next-generation sensors for satellites and creating new ways of storing and transmitting information. Because to understand our place in the universe, we need to understand what's going on Earth, but also the external forces that shape our planet and its environment. That's why the EARTHx is such a great series to help bring outstanding speakers who can provide us with unique perspectives on Earth and beyond. And this series, at its heart, every story you learn about is about the power of transdisciplinary science and how it opens up opportunities for the entire community. And on that note, I want to tell you a little bit about an amazing development that's happening right here, not just right here on Earth, but right here at the University of Calgary. In this year's provincial budget, the University of Calgary received commitment from the government to fund a new multi-science hub building right here on campus. And at the heart of this building is transdisciplinary research. It's going to be the most state-of-the-art science building in Canada. It will be the largest building or capital project that the University of Calgary has ever seen. And it's going to supercharge research. It'll allow us to bring an extra 2,000 students to campus. And I know you all really care about this because you're here tonight. On the roof of this new building will be new research facilities for space, aerospace, and astronomy. So I am super excited about this building, and I'm super humbled that the government of Alberta committed to this very large sum of money, because we are here to change and supercharge the Alberta economy, because the success of Alberta, past, present, and future, is all about science. And that's what we're here to do. We're here to get science done. And today was a very important day in the Faculty of Science because we, as a faculty, we voted in our next strategic plan, which is called Get Science Done. So we are going to do it and come back in 2030 and you're going to see something totally different than what you see here today. And it's truly going to be amazing. But what's going to be just as amazing is this talk that's coming up. So with that, I'm thrilled to invite Charles back up, and he's going to tell us about this amazing speaker we're going to hear. So thank you very much. Have a great evening.
Thank you, Kristen. It is fantastic to see the investments by the government of Alberta and by the Gallagher family to make this university a better university. It's important to invest in science. I'm pleased to welcome this evening's EARTHx speaker. Dr. Natalie Wette is an astrophysicist and an avid science communicator. Her research is on the formation and evolution of galaxies, particularly those found in groups and clusters, such as the Virgo cluster. She is the deputy director of EARTHx and of the Observatoire du Monde Magnétique, and is the outreach scientist for the James Webb Space Telescope in collaboration with the Canadian Space Agency. She earned her PhD at Queen's University in Kingston, Ontario in 2017, and has worked on telescope observation programs in Hawaii, New Mexico, Chile, and other locations around the world. She is active as an analyst, contributor, and speaker for various media outlets and organizations working to promote science and astronomy to the general public and to encourage the next generation. We are thrilled to have her here tonight to share some insights into the James Webb Space Telescope. Launched in 2022, the images from this telescope have instantly captivated audiences around the world. They recently captivated the students in my Geology 209 class, an introduction of geology for non-majors, as we considered the deep time origins of the universe and of our planet Earth. I am literally awestruck as I look at some of the clearest glimpses ever seen of the most distant and mysterious corners of our universe. To help illuminate those fascinating developments, please join me in welcoming Dr. Natalie Wette to her EARTHx talk, Seeing Beyond the Visible with the Webb Telescope. Natalie.
Thank you so much, Charles. Can everyone hear me? Perfect. All right, so it's my great pleasure to be here tonight to talk about the James Webb Space Telescope. I've braved snowstorms and canceled flights, but I've made it here in one piece. So really wonderful. Thank you for all the organizers, and very interesting for me to learn about the philanthropic funding for this series of events where I am at the Trottier Institute for Research on Exoplanets. We very much depend on philanthropic funding as well, and so it's wonderful to see the enthusiasm for science and for outreach events for science as well. So tonight we'll be leaving the Earth, we'll be going out into space. But first, let's sort of talk about astronomy a little bit in general. I always love to talk about astronomy as a very democratic science. So it's often talked about as the oldest science in the world. We've been doing it for millennia as humans. And one of the reasons why that is because fundamentally, you don't really need any instruments to do astronomy. You can simply step outside, look up at the sky, and see how things in space change over time, over seasons, over the years, and that's what we've been doing for a very long time. But obviously, humans are very curious, we want to know more, and so we've developed tools to try and understand the cosmos more deeply. So the tool par excellence for astronomers is, of course, the telescope. We've had telescopes for a few hundred years, and we've developed them, made them bigger, made them more sensitive. But one thing that's wonderful about modern telescopes is that they allow us to look at different kinds of light. So you may know about the electromagnetic spectrum, and it includes the kind of light that we can see, what we call the visible light, but it also includes plenty of other kinds of light that are invisible to the human eye. So here you can see these different kinds of light going from radio waves here, so very long wavelengths, through the infrared, the visible light, so the colors of the rainbow that we know, ultraviolet light, X-rays, gamma rays. Those are the very energetic, shorter wavelength types of light. And just because humans can't see in these kinds of light doesn't mean that the universe isn't shining in these kinds of light and telling us a very interesting and important story. So in order to understand the entire cosmos, it's important for us to develop tools that can look at these different kinds of light. And to convince you of this, let's look at one galaxy in particular, a spiral galaxy called the Whirlpool Galaxy. And here you can see the exact same galaxy as seen in different kinds of light. So if you had supercharged human eyes, you might be able to see a picture like this. This is an optical light, what humans can see. And really, the kind of light that we are very sensitive to when we're looking at optical light is stars that look very much like our sun. That's what they peak in, optical light. So you see all these wonderful stars littered all around. But if you instead look at infrared light, for example, you'll actually be more sensitive to colder stars, which are much more abundant, smaller mass stars. So you're seeing a whole different other population of stars. If instead you look at the ultraviolet light here, you become more sensitive to massive stars, stars that are much larger than the sun and much hotter. If you're looking instead in the radio or in the X-ray, you're looking at cold or hot gas. So different mechanisms essentially shine in different kinds of light. So if we only looked at visible light here, we would only see one segment of what's going on in the galaxy. So this is why we absolutely need to do what we call multi-wavelength astronomy, looking at different kinds of light. Unfortunately, we have a challenge as astronomers, and it is that for the most part, we will all stay on this wonderful Earth, protected by an atmosphere that blocks out a lot of this kind of light. So here you have a diagram with the electromagnetic spectrum again. On this axis here, it's flipped from what we saw before. So the very short wavelengths here, gamma rays, X-rays, ultraviolets, going through visible, infrared, and then radio waves. And the more brown you see for a specific wavelength, the more our atmosphere blocks or absorbs that kind of light. Now, you might know a little bit about X-rays and gamma rays, and you know that they're not too kind to humans. They actually damage our DNA. So it's actually a really wonderful thing that our atmosphere blocks out this kind of light, because there is that kind of light, that kind of radiation in space. And if we were to be bombarded by that kind of light, life would be very, very hard here on Earth. So this is a good thing in terms of our survival, but it's not so good for astronomers who want to understand what's going on in that kind of light. Really, when you're looking at this diagram, there's only two real windows in the atmosphere that lets light pass through. And it's in the visible light here, which is great, so we can see around us, and radio waves here, which we've leveraged essentially for all of our telecommunication system. But that means that for all the other kinds of light, if we want to understand what's going on, doing it from the surface of the Earth within our atmosphere is not a very easy thing to do. So I might ask you then, in order to look at these kinds of light, where would the best place to put a telescope be? And you might all think to yourself, well, space. And it's written in the name of my talk, the James Webb Space Telescope. So we are talking about space telescopes, of course. So there are lots of advantages in putting a telescope up into space, namely that you can look at these different kinds of light. However, it is also very challenging. You have to build these telescopes, put them on a rocket. It's expensive to launch a rocket into space. And then imagine something terrible happens, your rocket explodes, your space telescope is completely destroyed, and it has happened, not to me thankfully, but to some of my colleagues, and then you can't do anything. Or say you do have a successful launch, and then something breaks on the telescope. It can be very hard or even impossible to fix that telescope. So we continue to build telescopes and observatories here on the ground, especially in the visible light and radio waves. They're very complementary to each other. And if I say space telescope, of course, now I hope the first thing you think about is the James Webb Space Telescope, but you might also think about the Hubble Space Telescope, which you can see in the background here. So Hubble was really a huge revolution, launched in the 1990s, in 1990 in fact, and it is located close to the Earth, about 520 kilometers above our heads. So that's not very far. It's about the distance between Toronto and Montreal. And that means that we can fix it if something goes wrong. And it's a good thing because something did go wrong when it was launched. There mistakes, there were problems with its mirrors, and so it was fixed in 1993 using the first Canadarm with an astronaut repair mission. But it's been doing wonderful science ever since, and it looks at visible light. So you might ask, well, why did we put a visible light telescope in space if we're able to do that kind of science from the ground? There's still an advantage to be up in space. You don't have to deal with snowstorms or clouds or light pollution, for example. So it's still a wonderful telescope. But it's about to celebrate its 34th anniversary, and that is already much longer of a life expectancy that we had for this telescope. So as soon as the 1990s started rolling around at the very start of the Hubble mission, we were thinking about the successor to Hubble. And I say successor and not replacement because it is not our intention to put Hubble in early retirement. As long as it wants to work for us, we're going to keep it on board, so no problem there. But we wanted to think about what the next big telescope mission was going to be. At the time, it was called the Next Generation Space Telescope. I'm a huge Star Trek fan, so I was a big fan of that name. But eventually, it became known as the James Webb Space Telescope. And so the James Webb Space Telescope is, again, very complementary to Hubble. It's taking up a lot of what Hubble learned, and it's building up on that, but there are also lots of key differences between the two missions. So this is an international mission led by NASA with a contribution from the European Space Agency, and those were the two partners for the Hubble Space Telescope. Huge players, obviously, lots of funding. What's really exciting for us, however, is that the Canadian Space Agency is the third partner in this mission. And this is by far the largest space astronomy mission Canada has ever been involved in. Okay, to be fair, it is the largest space astronomy mission ever done by humans. So that's the case for the other space agencies as well, but it's really a huge step forward that Canada was solicited to be a part of this mission. And I very much hope that we will be involved in the successors to the Webb Telescope as well. So as mentioned, I'm the outreach scientist for the Webb Telescope in Canada. This type of role is relatively new. I'm part of the science team, so we're about a few dozens, about 60 astronomers in Canada who have worked on the telescope and who are now very active in using data from this telescope. But my role really is to act as a bridge between the science team and the general public. So it's public funds that allows us to be part of this mission. So really, this is not a telescope that only belongs to astronomers. It's a telescope that belongs to all of us and all of you. So it's very important for us that everyone can appreciate the work that the telescope does, its beautiful images, and understands the breakthrough science that it's doing. So as outreach scientists, I've had the absolute pleasure to see the telescope, obviously before it was launched into space. I would love to visit it in space, but that would be difficult. So I visited while it was being tested in a clean room in California in 2019, and you can't really get a good sense of how big this thing is from this image until you see this little human right here. So you can see how gigantic this telescope really is. I like to call it sort of like a small 3-story house floating up in space. So its sun shield here is about the size of a tennis court. Its mirror, which is folded up here, is 6.5 meters wide, absolutely gigantic. The largest space telescope we've ever launched into space. So I love this picture. I love this trip that I took. But the picture that I usually really show to prove my commitment to this mission is this one here instead. So my partner is actually a big fan of Halloween, and he's been constructing giant cardboard costumes for Halloween for the last 15 years. And so I was inspired by both him and the James Webb Space Telescope. So just a few months before launch for Halloween, I built this cardboard scale model to scale. I did all the measurements of the telescope, and I wore it for Halloween, and I gave out candy. And so this is something that I love about my job. I get to sort of inject my personality in how I do outreach. And I love showing kids how you can do outreach and science in lots of different ways. And science is fun. It doesn't have to be boring. It's not just math and equations and all that stuff. Science is fun and exciting and passionate. And you can be a scientist too and do it in your own way. So just a few months after my Halloween costume, finally the launch of the telescope took place. It was on Christmas morning, December 25th. We didn't plan it to be Christmas morning. That was just the window of time when it needed to happen in 2021. And so I'm going to go ahead and play a few seconds for you of the liftoff of the launch of this telescope.
T-minus 30 seconds and counting. Standing by for terminal count.
Who watched it live?
À tous de DDO, attention pour les décomptes finales. 10, 9, 8, 7, 6, 5, 4, 3, 2, unité, top.
And we have engine start. And
Allumage
liftoff.
UAP, décollage.
Décollage, liftoff from a tropical rainforest to the edge of time itself. James Webb begins a voyage back to the birth of the universe. Punching a hole through the clouds, 20 seconds into the flight, good pitch program reported.
Trajectoire est nominale.
Vehicle performance is nominal. The Ariane 5 rocket continues to fly uphill in nominal fashion.
So I promise the French is not the French-Canadian me trying to contaminate you or anything like that. The launch actually happened from Kourou, which is in French Guiana in South America, and it was one of the contributions of the European Space Agency. So Arianespace is the company that provided the Ariane 5 rocket, and the launch pad was done in Kourou. So it was a wonderful launch. And lots of us were excited to go there to see the launch. Some of us were supposed to be at the Operations Center, which is in Baltimore. But you might remember in 2021, we were all in war with a little certain virus that kind of ruined our lives. And it was just at the peak of the Omicron wave of COVID-19. And so the majority of the team actually had to cancel their flights. Only a few very key people went to Kourou to see the launch, including the PI, the principal investigator of the Canadian instrument. So I was very glad for that. He spent like 25 years of his life working on this telescope, so it was fantastic. But for the rest of us, we kind of had to watch it from home. We were connected to the comms link on our computers and everything, but we were all disconnected physically from each other. A lot of us were still wearing like our polos, like our flight team polos. And so my partner had the idea to still try to commemorate the event. And so he installed his little tripod with a camera to look at us and our reactions of the event. I won't play that video, but I'll show you one screenshot to sort of convey how emotionally attached we become to these missions. So this is me at a very crucial point in the launch where the rocket fairing peels off and the telescope is totally exposed to the environment around it. And so I was very nervous. Obviously, it did it at the correct time. There was no real danger. But yeah, this is like the work of over 10,000 people, $11 billion, and 30 years of work that's just being strapped onto like a nuclear reaction and blasted off into space. But luckily, everything went wonderfully with the launch. So much so, in fact, that we saved on fuel and were able to prolong the lifetime of the mission from an estimated initial 10 years to now 25 plus years, at least in terms of the fuel. So that's really fantastic news. So of course, the launch is only the start. The James Webb Space Telescope is a very complex machine, arguably the most complicated machine humanity has ever constructed, certainly to launch it into space. And it was so large, in fact, that it needed to be built so that it could be folded up on itself in order to fit inside the Ariane 5 rocket, which at the time was still the largest, most reliable rocket that could be used to launch it into space. So if it was folded, that means after launch, we needed to unfold it for it to work. So this is a process called the deployment that needed to go on for 14 days. And we called this in the team the 14 days of terror. If you know a little bit about the Mars launches, there's the 7 minutes of terror, which is how long it takes for the Mars landers to land. And so, but we had 14 days to tolerate with this, so much longer. And you can't do this when the telescope is just parked next to the Earth. The telescope is moving towards its final destination, 1.5 million kilometers from the Earth, 4 times farther away than the Moon. So you need that initial boost from the rocket launch, that momentum. You can't lose it. So as this is going on, the telescope is continuing to move towards its final destination. And there's no less than 300 mechanisms that needed to unlatch for this deployment. And each of those mechanisms is something we call a single point failure, meaning if one of them failed, the entire mission failed. So this is why we were terrorized for 14 days. But luckily, this again went wonderfully well. There was one step I would say that was especially worrying for many of us, and that is the deployment of the sun shield that you can see here. So one big difference with the Webb telescope compared to Hubble is that it looks at infrared light, not visible light. So that means it absolutely needs to be in space in order to function. And infrared light is very sensitive to heat. So that means if the sun were to heat up the mirror and the instruments of the telescope, it would start radiating in infrared light itself, essentially causing its own light pollution. So the sun shield was completely necessary in order for this to work, to protect this part of the telescope. And so the sun shield was something that caused us quite a bit of issue in the testing phase, and that component alone had 132 mechanisms. So that was a little bit worrying. And then you have the deployment of the mirror as well. Again, 6.5 meters wide, made up of 18 separate hexagonal segments that all can be moved independently, all covered with a thin coat of gold, the real metal gold, because that reflects infrared light very, very effectively. So after 14 days of terror, the deployment went very well and we were very happy. An extra 2 weeks to get it to its final destination. And that's where it is now, orbiting an empty spot in space called Lagrange 2, or L2, that's always 1.5 million kilometers behind the Earth. So it's been working very well since then. After this 1 month of deployment and getting to the final destination, there was an extra 5 months of something called commissioning. That's when we turn on all the instruments, test them, make sure they all work, align the mirror, and then we can start doing all of our technical observations and scientific observations. And in order to do that, you need science instruments. So here you have the instrument module that's in a box that's behind the mirror. So the mirror is like wearing a little backpack, and it holds 4 instruments inside. So these instruments were all contributed by the different space agencies. You have a combination of cameras, a special kind of tool called a spectrograph, and you have the Canadian instrument right here. It's called FGS Nearest. It's a double instrument. And because it's at the center, at the heart of the instrument box, Canada needed to deliver its instrument first in 2012 so that everybody could pile onto it. And across these 4 different instruments, there's 17 modes of observations. That means 17 different ways that the telescope can take data and take observations. So lots of different kinds of science. And there is some redundancy between the 17 modes in case something breaks, another instrument can pick up the slack, for example. So these 4 different instruments are all looking at infrared light, but just like visible light can be broken up into the different colors of the rainbow, infrared light can be broken up into different types of wavelengths as well. So 3 instruments, the ones that start with N, are all looking at the near infrared. They overlap the red end of the visible light a little bit too. So all of these are looking at the near infrared, and you have one instrument called MIRI, and it's looking at the mid infrared, so longer wavelengths. And they can all do this because of that sun shield that I mentioned. The sun shield is able to cool passively the telescope to a temperature of minus 233 degrees Celsius. Even for Calgary, that's cold. That's very cold. That's about 40 degrees above absolute zero. But because the mid-infrared is a little bit more sensitive to heat, it has an additional refrigerating system on board so that it can cool down its operations to minus 267 degrees Celsius, or 7 degrees above absolute zero. So it's a little bit trickier as an instrument. So it's looking at infrared light, but that means that when we show you an image, we have to figure out a way to make that infrared light visible, comprehensible. So here's a little tutorial on how to make these space images. And I often find, unfortunately online, people are saying, these images are fake, everything is CGI, NASA didn't really go on the moon. That's very depressing to hear. But the fact of the matter is, if we simply showed you an infrared image, it would not be very satisfying because it would be invisible to your eye. So we need to do a little bit of manipulation in order to make it visible. So one thing that a lot of people don't know is that space telescopes don't actually see in color. Even visible telescopes, they don't see in color. They all see in black and white, essentially. But they can see black and white in a bunch of different color bands or wavelength bands, essentially, simultaneously. So when a telescope is looking at a part in space, it will be able to capture that in as many bands as you construct, essentially. So for example, if we have 3 bands, one is named F90W, one F200W, one F444W. Those numbers are telling you the wavelength of the color that you're looking at. Here you're looking at 900 nanometers. Here you're looking at 2,000 nanometers. Here, 4,500, or 2 microns, 4.5 microns. That is the kind of color that you're looking at. And the black and white intensity is then essentially telling you what the intensity of the image is at that particular color. But these are not colors of the rainbow. These are beyond what we can see as humans. So then it's our job as astronomers working with artists to assign a color to these different invisible wavelengths. So typically what we do is we transpose all the colors of the rainbow onto a sort of rainbow in the infrared. The shorter wavelengths will stay blue, the longer wavelengths will stay red. So here we have, for example, all these 6 different colors in infrared colors, but we are assigning them colors of the rainbow in what we call chromatic order. We respect the order of the colors of the rainbow. So you could imagine putting that one blue, the middle one green, that one red, and then we combine those different images and those different colors together to make a color image like this. So this is actually quite close to what we would be able to see if we had infrared vision. And we try to respect the nature of the structures and the chromatic order, as I mentioned, but we have to do a little bit of manipulation. Otherwise, we wouldn't be able to see anything. So this is how we create all these different images. So that's sort of like a technical overview of the telescope. But of course, we want to do science with it. So what is the Webb telescope observing? And one thing I love about Webb is that it is a very generalist kind of telescope. Some telescopes are very specialized. They only look at exoplanets, only look at black holes. But if Webb was a doctor, it would be a family doctor. It would have to know a little bit about all the different kinds of things. So we can sort of break up what it does into 4 main categories. The first of which is alien worlds, always very catchy with the media and little kids. And alien worlds can mean worlds in our solar system, but it can also mean exoplanets, worlds that are beyond our solar system, planets that are orbiting stars other than our sun. And that is a very new field of research. We've only been able to really detect exoplanets for the last 30 years. And Hubble was even launched before the very first exoplanet was detected. It's done good exoplanet work, but it was never designed specifically to study exoplanets, whereas Webb, the instruments aboard were designed specifically to study exoplanets. So we've never had such a specialized tool to do just that. We can also study the life of stars. The life of stars has a lot of key moments where you have lots and lots of gas and dust, and that can be a real challenge. Imagine trying to see a phenomenon through a bunch of gas and smoke and dust. You can't really see what's going on behind it. But that's where the power of infrared comes through, and I'll show some pictures to explain that. Similarly, we want to understand how galaxies evolve over time, and these evolve over many billions or even tens of billions of years, but they often don't evolve alone. They're often found in groups or in clusters, like what I study. And in those clusters, just like humans and animals, they will interact, sometimes nicely, sometimes not so nicely. And you can see how those interactions changes the evolution of those galaxies over billions of years. So we want to study galaxies throughout the entire history of the universe, all the way to what we call the primordial universe, or the early universe. So one of the main goals in building Webb was to look farther back into the history of the universe than ever before. And we can do that because telescopes are also time machines. Because it takes a long time for light to travel the vast distances in space, by the time we capture the light of a very distant galaxy, say 10 billion light years away, it's taken 10 billion years for the light to get here. So we're not seeing the galaxy as it is now. We're seeing it as it was 10 billion years ago. We're seeing a snapshot of the past of that galaxy. And with Webb, we want to look as far back as possible in the history of the universe at those very first few galaxies created just a few 100 million years after the Big Bang. So I'm going to give you a little bit of a sample of my favorite discoveries up until now from Webb. If I were to cover everything, I'd be here for weeks. So I do apologize if I didn't include your favorite Webb discovery. If you want to know more, I'm going to give you a link at the end where all of the different images and press releases from the Webb team are included if you want to explore. So let's start close to home. Let's start a little bit in our solar system. And there's two planets that I always like to feature especially, and that's Neptune and Uranus, our ice giants. And I often like to call them the forgotten siblings of the solar system. And that's because they are the only planets in our solar system that have never had a dedicated probe mission. We've had things go around Mercury and Venus. Mars has lots of robots that's been there. There's the Juno mission around Jupiter right now, which is really fantastic. There was the Cassini mission around Saturn. Even Pluto, which is not really a planet. I still love Pluto, but it is a dwarf planet. Had the New Horizons probe take a very nice long look at Pluto. But Neptune and Uranus, all they got was a flyby by the Voyager probes in the 80s, and that was over 30 years ago. So when you see really nice pictures of Uranus and Neptune in your textbooks or online, that was probably taken by the Voyager flyby, and we haven't had a lot of close-up looks of these worlds since then. We've really relied on Hubble and some of the very largest ground-based telescopes that have 10-meter wide mirrors on Earth. But now that we have Webb, not only can we have a closer look at these worlds, we can look at them with a new viewpoint in the infrared light. So this is a composite image. Obviously, these planets are not close together in the solar system. And you can see here Neptune and Uranus. So this is more of a zoomed out version of Neptune. You can see Neptune there with its rings, 7 of its 14 moons, and its most important moon, Triton, which is very, very bright in the infrared. Whereas because these are ice giants that have lots of methane and other gases in their atmospheres, they actually absorb quite a bit of infrared light. So they actually look dimmer than some of their moons. But you can still see lots of details in the cloud formations, for example, inside of these different worlds. If we look at Uranus instead, we can actually see some information about the colder poles that look kind of polar, like sort of an ice cap, but it's not really an ice cap like we have on Earth. And you might think that I've messed with the orientation of this picture, but no, Uranus is the only planet in our solar system that rotates on itself with a horizontal axis. So all the other planets have a vertical rotation axis, just like Earth, but we think at some point in Uranus's past, it got bullied by an asteroid, it got knocked over, and now it's sort of rolling on its belly, and it's taken with it its rings. So its rings really are oriented in this direction there. So you can see Saturn is not the only world with rings. You have a beautiful ring system around Uranus as well. And people who are really interested in Neptune and Uranus now have the chance to see not only how these planets have changed over the last 30 years, but they have a reliable tool where they can take observations of these worlds regularly to see seasonal changes on them. Think about how much the Earth changes on a yearly basis. And they can have that kind of time and opportunity of study for these ice giants. Moving further away now, looking at these exoplanets that I mentioned, these are worlds beyond our solar system. So I mentioned the challenge in observing Uranus and Neptune, which are within our own solar system, albeit quite far out. Now imagine trying to study a planet that is tens or hundreds of light years away. That is a huge challenge. Not only are they far, they're orbiting stars that are much brighter than themselves, so they get lost in the glare of their stars very easily. So when you see an image like this one, unfortunately, it is not a real image. It's what we call an artistic representation. But that doesn't mean that we're just sort of guessing in the dark. We can actually tell a lot of information, especially now with Webb, what these worlds might look like. So we can tell what their size is, their mass, and if you have both size and mass, you can tell their density, which tells you something about their composition. You can tell how far they are from their star, which tells you about their temperature. We can even start treating these worlds like 3D worlds, where we can tell the difference between the day side and the night side of the exoplanet. There was even an exoplanet that was studied by my colleagues at the University of Montreal last year, which showed evidence of volcanic activity. This is something that's tens of light years away, but we have good reason to believe that there are volcanoes at the surface of these different planets. So we can really treat these like worlds of their own, and it's really wonderful, and Webb is a big part of being able to do that. So I'm part of this wonderful institute called the Trottier Institute for Research on Exoplanets. We're about 80 different researchers scattered across a few institutions in Quebec, mostly at the University of Montreal. And yes, these are people that observe exoplanets, but we also have an experimental astrophysics lab where we build the instruments we need to collect the data that we need. So in part, we were involved in developing the Canadian instrument aboard the James Webb Space Telescope. And that's one of the reasons why the Canadian instrument is a really good tool for exoplanets specifically. We kind of baked in our own personal interest in the instrument. But we've also built different instruments that have been deployed across the world in observatories in Chile, in Hawaii, to do wonderful exoplanet science. This is all in the goal not to move to these exoplanets, but to better understand how unique the Earth is compared to the diversity of planets that exist, and also better understand sort of the past of the Earth and other ways that planets can form. We can't turn back time on Earth. We can do different things, like look at fossil records in asteroids. We can look at fossil records on the Earth, but it can also help to see other planets at the beginning of their formation and try to get hints from that at how Earth could have come to be. So in order to look at an exoplanet, I mentioned, it's very, very challenging. So how do you spot an exoplanet? You have to be pretty tricky, pretty clever. And the best way, the most efficient way to do this is with something called an indirect method. So you're not really looking at the exoplanet itself. You're instead looking at the effect of the exoplanet on its star. And the best way to do this is called the transit method. And this is something very similar to something that's going to happen soon on April 8th. 2024. I don't think it's a very deep eclipse here, but in Montreal, we're in the path of totality, so we're very excited for that. So instead of having a moon passing in front of our sun, we can see an exoplanet passing in front of its star. So we have specialized telescopes, not like Webb, other telescopes, that stare at hundreds of thousands of stars simultaneously, and they can see a dip in the brightness of those stars. And if it keeps staring at those stars, it may see that dip come back periodically, which is a good indication that there's something orbiting that star that is blocking the light. So unfortunately, we can't see a black dot moving across the surface of the star. Really what we see is this graph here. But that graph can tell us great information like how frequently that dip happens, which tells us the period of the orbit of the planet, and how deep that is, the dip, tells you how big the object that blocked the starlight is. So that tells you how big the exoplanet is. So in using this, we're able to spot the exoplanets, we detect them, and then we find that they're good candidates and ship them off to Webb so that they can be analyzed further. And in order to do that, we can use the magic of spectroscopy to get really into the details of what is going on that exoplanet. So in order to explain spectroscopy, I just need to talk about Pink Floyd. So essentially, it's very simple. You just need an instrument like a prism or a spectrograph that can take light, break it up into its constituent colors, and then you get lots of information in that rainbow. So you can do it with white light, like from the sun. You break it up in a prism, and you get all the colors of the rainbow. But you can do this with any kind of light. You can take infrared light, break it up into an infrared rainbow. So you can do this, for example, with any star. And here you have a spectrum from our star, the sun. So you can see all of the colors of the rainbow, but you might also see some little black marks scattered throughout. And what is happening here is that the light from the sun's heart is passing through the atmosphere of the sun, and certain specific molecules and atoms are absorbing very specific colors of that light and leaving these little marks. So these little marks are essentially a chemical fingerprint of the medium within which the light passed through. So you can do this with a star. In the case of an exoplanet passing in front of a star, imagine that that starlight is passing through the atmosphere of the exoplanet. You can do the same thing. You can read that fingerprint, that chemical fingerprint of the atmosphere of this exoplanet, hundreds of light years away, and understand what is inside that atmosphere. So we've done this with many different exoplanets already, but one that's been especially exciting is called K2-18b, and this was a study released last fall. And it's exciting because it is a world that is in the habitable zone of its star. That means the temperature is right for it to contain liquid water, and indications are that it could be what we call an ocean world. So if you imagine Waterworld starring Kevin Costner, it's a world completely covered by a liquid ocean. And when we talk about liquid water, to us, that's a really good indication that there is potential for extraterrestrial life there. So we did this study. We looked at the chemical fingerprint of K2-18b's atmosphere. And we could make it a rainbow, of course, an infrared rainbow, but we love our graphs. And so basically, all the little black marks that you saw in the fingerprint is the equivalent of these bumps that we can see in this diagram. And so you can see the evidence of specific molecules in the atmosphere of this exoplanet. So we were able to detect certain things like methane, carbon dioxide. But one particularly interesting molecule is called dimethyl sulfide, or DMS. It's not a well-known molecule. But what's interesting about it is that here on Earth, it can only be created by one thing, and that is organic life, biological activity. Now, does this mean that this is proof that aliens exist? Unfortunately, we're not there yet. So this was a relatively weak signal, and that's often what happens in science. In science, you need to have a robust measurement that is remeasured many times by many different teams and many different instruments to show that it is a real signal. And we're not there yet. We need to do more studies about this world. Another challenge is that just because on Earth it can only be created by life, doesn't mean there's not a weird kind of geological process that does not require life on this alien planet that can produce DMS. So here is starting to glean the real complexity that's involved when we say we're looking for alien life. Unless we literally are getting a radio message saying, "Hi, I'm an alien," it's not that simple. It's going to be very iterative, and we're going to need lots of measurements and try to weed out what is a true positive versus what's a false positive. Now, if you move to stars instead, stars are born in these giant star-forming regions in nebulae. And this one here is called the Pillars of Creation. And this is my favorite picture taken by the James Webb Space Telescope to date. So within this big structure, you have the formation of lots of newborn stars. You can see them mostly embedded inside the dust in these sort of reddish areas at the tip of the fingers here, right here. But really, I find that the beauty of this picture is truly unveiled when you compare it with a very iconic image that was taken by the Hubble telescope. So I grew up with the Hubble telescope in the 90s. Those pictures really made me want to become an astrophysicist. And here you can see the stark difference of the view that you have between the Hubble telescope in the visible and the Webb telescope in the infrared. And of course, the Webb image appears sharper, but the thing I really want to drive home is that suddenly all the gas and dust that is sort of blurring your vision in the visible light is sort of peeled away in the infrared. And that is because infrared light can pierce through that veil of gas and dust. And the start of the life of stars is very, very dusty. So in order to see stars being born, you need this infrared light to look at the first few moments of a star's birth. So you can really see this comparison. You can also look at the birth of individual stars. So these are what we call protostars, or this is a specific kind of protostar called a Herbig-Haro object. And the birth of a star is not a quiet time. You have the collapse of a giant molecular cloud, and at the center of that, you have the formation of the star. You might have the formation of planets as well. But not all of the material quietly settles into the star. You have a huge ejection of material and energy at the poles of the star. You can see them in these two images. You have sort of like these jets or this sort of hourglass shape here. And to give you an idea of the intensity, the violence of these jets, to give you a sense of scale, if you see a little thin black line about this width right there, that's about the size of our solar system. So at the start of our solar system, this is what it looked like, we think. We have the sun at the very center collapsing with all of our planets being formed in this disk and these huge jets protruding out of the system. Eventually, these stars, they die, and depending on how massive they were, they will have very different deaths. So about 95% of stars that are a similar mass to our sun or smaller will die in what we call a planetary nebula. At the end of its life, it will puff up into what we call a red giant, and in a final death sneeze, it will blow off the external parts of its envelope. And this is what you see here in the Ring Nebula and the Southern Ring Nebula. These shells of material are these successive death sneezes of the material being blown off. And all you're left with, at the very center, is the cadaver of the star, like a zombie star. That's called a white dwarf, that no longer has any nuclear fusion. It's been compressed, so it's still very hot, 100,000 degrees, but it just becomes cooler and cooler as time goes on because it can no longer create its heat. If instead you have a more massive star than the sun, much more massive, it's a more explosive death. It dies in a giant explosion called a supernova explosion, and when that happens, that single explosion is brighter than every other star in the galaxy combined. So it is a really bright event that we really take notice of, that gives us lots of information about the life of that star. So this is what happens here. It explodes, and what you have left is what is called a stellar remnant. It's a kind of nebula. And all of this material you see here is basically the guts of the stars that's been blown out in all directions. And you still have a cadaver left at the center, but it's more exotic. It's either what we call a neutron star, or in the case of the most massive stars, you create what we call a black hole. A black hole that is so intense, that is so dense, that nothing can escape it, except, not even light. Nothing can escape it. But all this material being blown away is not wasted. It will be mixed together in interstellar space and eventually will form other stars. So these stars are very nice, efficient recycling factories. If we move instead to galaxies, I mentioned galaxies, they like to live together in groups. So these are two instances of how galaxies can interact with each other. Here you have the cartwheel galaxy, which is a very rare type of galaxy called a ring galaxy, and you can see why. But it was not always like this. What happened actually is that this little guy, this companion galaxy, cartwheeled through this big galaxy, and that interaction caused a huge explosion of new stars being formed in the shape of a ring. So because of that interaction, it completely changed the type of galaxy this was. So you can see the really deep interactions going on with the evolution of these galaxies. Here you have two galaxies that are not physically interacting, but their light is interacting. In the background, you have what we call an elliptical galaxy. It's shining brightly, and in the foreground, a spiral galaxy. But because this galaxy is shining through the material of the front spiral galaxy, you have that same kind of effect that we saw with an exoplanet passing in front of a star and the starlight telling you the chemical fingerprint of that planet's atmosphere. The light shining through the spiral galaxy can give you information about the chemical makeup of the galaxy in front. You can have larger groups of galaxies. This is called Stephan's quintet. You have 5 galaxies here, 4 of which are interacting. These two are basically almost done merging together, and you have this one careening down. And again, these galaxies interacting is causing the birth of new stars. So the orange you can see here is a huge gas shock wave as the gas shell around these galaxies is compressing, causing the birth of new stars. But if you really like galaxies, this is the picture for you. This is called the Webb Deep Field of Galaxies. It was the first image ever released to the public on July 11th, 2022. And within this picture alone, there are 7,000 galaxies. I didn't count them myself. We have algorithms to do that. And you might wonder, okay, well, is this a huge part of the sky, a huge part of the universe? And in fact, no, it's really not. The area in the sky covered by this picture is the equivalent of 1 grain of sand on the tip of my finger held at arm's length. That little part of the sky holds these 7,000 galaxies. And they're all different kinds of colors and different shapes and sizes. Some are closer to us. The ones that are quite white, they're closer to us. They're about 4 billion light years away. And the ones that are farther back, the smallest red dots, are up to 13 billion light years away. And if we take a look at how different this part of the sky looks with Hubble in the visible and Webb in the infrared, you'll see that there's a lot more stuff going on in the image taken by the James Webb Space Telescope. And you might think, well, this is because it's a larger mirror, it's a more powerful telescope, but that's not the only reason. Several of the galaxies visible in this image are invisible to Hubble, ironically, in the visible light. And that's because of a phenomenon called redshift. So we live in a universe that is expanding, and as the universe expands, galaxies are moving away from us. Galaxies, they tend to shine quite brightly in blue light, even ultraviolet light for the very first galaxies. But as these galaxies move away from us, that light is being stretched from the blue and ultraviolet light into red light, into infrared light. So in fact, for us to observe it, we absolutely need an infrared telescope. These galaxies are invisible to a telescope like Hubble. So that is one of the reasons why we conceive the James Webb Telescope as an infrared telescope. Taking a closer look again, you might see some of these galaxies look a little bit odd. They look sort of stretched out and warped. If we take a step back again, you'll see that a lot of these stretched out warped galaxies kind of look like pieces of concentric circles that are all centered around this point here, this really bright, larger galaxy. And you would be right. These are sort of forming these arcs around the central galaxy. And this is not really what these galaxies look like. They are deformed by a phenomenon called gravitational lensing. So these foreground galaxies are so huge, so massive, that they can actually warp space-time, the entire fabric of the universe, and the light of the background galaxies that we're observing. And because it's warping that light, it causes them to form these arcs. And if everything is perfectly aligned, you can actually create something called an Einstein ring. So you might think, okay, that's not really cool. I want to be able to look at my galaxy as it really was. So it's true, we do need to work to try to piece the galaxy back to its initial form. But that gravitational lensing effect can also act like a magnifying lens. And so often, these galaxies, yes, they appear warped, but they can appear tens or even hundreds of times brighter than they originally would, giving us sort of like this cheat code to look at galaxies that would otherwise be much too faint. You might have heard also of something called the redshift race. Everyone is trying to find the oldest galaxy, the most distant galaxy. And already after only 6 months of observations at the end of 2022, we were breaking the records set previously by Hubble. So redshift is a measure of how distant these galaxies are. And these two here, with a redshift of about 13, we're observing them when the universe was only 2% of its age. So we're getting closer than ever before to the very start of the universe with the very first galaxies. But you'll notice it's a little frustrating that there's these little red dots. And that's sort of what we've had to tackle for the longest time, studying the very early universe. But with Webb, we are now able to study very, very young galaxies with the kind of detail we've never had before. And we're finding shapes of galaxies that are not really like what we have in our local universe. So this was released a few months ago. I think whoever did it was tired of winter and had their mind on summer. They sort of, as a joke, started talking about surfboard-shaped galaxies and pool noodles and frisbees and volleyballs. But essentially, we have the capacity to look at the detail and the shape of these distant galaxies to understand not only their shape, but even study individual knots of star formation, despite them being 10 billion light years away. So it's really a huge revolution in space astronomy, and space exploration, but it's really just the start. As I mentioned, we've only been at it for about 2 years. We hope this mission will continue for 20 plus years. And even beyond that, we're already working on the successor to Webb. And Canada is along for this ride, so stay tuned because the best is yet to come. Thank you.
Thank you, Natalie, for an amazingly inspiring talk. The images are just amazing, and now I feel really humbled about what I said in my lecture a week ago about the origins of the universe. But there's just so much to learn out there, and it was obvious that you have an amazing passion for your science, and the image of you as all that instrument was unfolding in space, and how much was tied to that is absolutely amazing. And I was also very pleased to learn that you are a Star Trekkie too.
Star Trek, not Star Wars.
That's right. That's right. Okay, so thank you again, and thank everyone that's, thank Natalie for a fantastic talk.
Thank you.
Now, I am sure that many of you have questions for Dr. Ouellette. So just a reminder that if you are online, is the number up there? Yes, there it is, 403-708-5749, and Owen will be reading those questions out. And we have, Annie is going to be taking the mic around the room. So we now have some time for questions.
All right.
We'll
I can.
We'll start in the room here.
There you go.
For a couple.
Hi, thank you so much, Natalie. I believe last month I saw a paper had been published showing that the James Webb had directly imaged some exoplanets around a couple of white dwarf stars. You mentioned indirect imaging. I'm wondering if you would be able to go into a little bit of detail about direct imaging then?
Absolutely. I was putting down my water bottle when you started talking, so I don't actually see where you. Oh, there. Okay, perfect. Okay, I want to make eye contact with you. Perfect. Yeah. So in certain cases, it is possible to take a direct image of the exoplanet. It doesn't look like the planets in our solar system. They look like bright dots, relatively bright dots orbiting brighter dots, essentially. But it's only in specific cases. When it's orbiting a white dwarf, that helps because the white dwarf is dimmer. It also helps if the planets are larger. If they're younger, they tend to be brighter, and if they're far away from their star, because something we need to do is block out that central star using a technique called coronography. So we're essentially just putting a mask over the central star in order to take a picture of the planet itself. And so we can do that. We could do that before Webb. But now, with the Webb Telescope, we're able to look at smaller exoplanets. Really, before Webb, we were looking at what we call sort of super Jupiters that had masses that were several times that of Jupiter. But now, with Webb, we are hoping to bring that down to Saturn mass. So really, we're pushing the limit as to what kind of planet we can directly observe. And the successor to Webb that is currently in discussion is called the Habitable Worlds Observatory. And with that one, we would hope to be able to directly image Earth-sized planets. So basically, look at an Earth analog, but in real light. So that's very exciting.
Do we have one more for the room? Are we getting some online? Okay. One more from the room? We'll have more time here too.
How quickly does information transmit from the telescope to Earth?
So it's transmitted using radio waves, which go at the speed of light. So that only takes about 6 seconds to travel those 1.5 million kilometers. That being said, we have to share the NASA Deep Space Network in terms of how we can communicate with the telescope. So we usually, unless there's special circumstances, only have one downlink per day.
We had a question here from this young man right here, and then we'll go online. That's you, yeah.
So why can't you use different wavelengths of light? I mean, I know visible is out of the question, but why can't you say use gamma or radio waves?
So we have special telescopes that look at those different kinds of light. Different kinds of light require different special types of instruments. It's very hard to build an instrument that can look at all the different kinds of light. So we've made the Webb Telescope to be a specialist for infrared light. But for example, there's another telescope called Chandra, which is an expert at X-ray light. So each telescope is sort of a specialist, and they all work together to take images of the universe in different kinds of light that we combine after. Good.
All right, question in here from viewers of our live stream. First one up. Question is, how does the telescope and especially the heat shield deal with the potential impact of debris in space that could damage it? Is there a plan in place if that happens?
Yeah, so sometimes when you look at sort of diagrams or pictures, you have the impression that the solar system is littered with space rocks. It's quite empty out there, but there is some danger, and in fact, we predicted in our simulations that on average, 1 micrometeorite would hit the telescope every month. So really, we planned that into the selection of our materials to make them quite resistant to that impact. That being said, we also have another contingency plan where, because the mirror, it's really the mirror that's the main issue. We really want to keep it pristine because the mirror is composed of 18 different segments that can each be moved independently. If something were to hit the telescope to sort of change the surface of the mirror, we can move the different segments around to sort of change the shape of the mirror and compensate for that. So this is a flexibility that we have that we didn't have, for example, with the Hubble telescope, which had an issue with its mirror because its mirror was just one big monolithic piece. So we have contingency plans, but obviously we don't want to be hit by a big asteroid because then we can't fix it.
Another one, Owen?
Yeah, absolutely. Can you talk a little bit about the 13.8 billion light-year horizon, and do you think we're going to see galaxies from beyond that change our perspectives on the history and age of the universe, or just that whole piece? Can you tell us a little bit more about it?
So there's been a lot of, I could say, controversy or at least sort of surprise in the very early galaxies that we've observed. So we have lots of evidence that tells us that the universe is 13.8 billion years old. We would need a lot of evidence to counter that, to really flip the paradigm as we know it now. But one thing that we're finding with the very early galaxies we're observing is that they look too evolved, too mature for us to really make sense of it. It's like, imagine you're walking into a hospital and you're going into a nursery expecting to see a bunch of newborns, and you see a bunch of teenagers in there and you don't understand why. That's essentially what's happening now. So we're sort of like stuck now. The nuclear option would be to say, okay, the universe is actually older than we thought, to give these galaxies enough time to mature, but we're not there yet. Likely what is going on is that there's something about how galaxies evolved in the very early universe that we don't understand. We've set certain limits as to how efficiently, how quickly a galaxy can grow and build stars, and that doesn't mesh with what we're observing. So it might be that galaxies were a lot faster and more efficient at building up their mass than we initially thought. That's more likely to happen.
Another question from the room here.
Thanks. Can you explain how and how often the decisions are made on what the instrument is going to do?
Yeah, so this is a pretty typical process that we do for nearly all the telescopes, both on Earth and in space. We have calls for the entire community, the astronomical community. They're usually every 6 months or every year. And essentially at that point, astronomers team up, they write these proposals, and they try to write them really convincingly, saying, I want to look at this with this much time using these instruments to answer this question. Please, 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 please give me some time. And then after that, all of those get sent off to what we call time allocation committees, and they rank them. And then depending on how many hours they have available to give that year, some amount will pass through. And I've been on some of those time allocation committees. And just because we say no to a proposal, it's not because it's not good. It's because everyone is so good, but we have a very limited amount of time. We just released the program for the third year of operations, and to give you some insight, we had to say no to 8 out of 9 proposals received, and it's not because they were bad. But it's a competitive process that we do every year.
Okay, can we have another one online? And Annie, there's a question at the back there right after.
Absolutely. So a related question relating to the age of the universe there and what we can see. Using the James Webb Space Telescope, how far back can we look in time relative to what we thought might be possible? And is there the potential to advance that horizon further with any future telescopes that are underway?
So with Hubble, we pushed it to about 500 million years after the Big Bang. Our hope with Webb was to push it to 250 to 350 million years after the Big Bang. And we've basically gotten there in just 2 years of operation. So we do have some hope to push it farther. The telescope is proving to be more sensitive than we had predicted, which is always a nice thing. But we would really need a much bigger mirror to push it significantly farther back. But there's also a time period in the early universe called the Dark Ages, between sort of like the very early universe where there was a Big Bang and then this like soupy mess of atoms all around, and the very first stars being born. Between those two moments, there's just sort of like nothing, not nothing happening, but like nothing that's easily observable. So pushing into the Dark Ages wouldn't necessarily be that satisfying. Yeah. But with a larger telescope, we would hope to see the first stars rather than just the first galaxies.
Hi there. So I was just wondering, that kind of almost touched on what I was going to talk about. With all the technological advances of the James Webb, what is the next barrier? Are we looking at, when you're talking about Habitable World Telescope, are we looking at remaining the IR? Where's the barrier going to be? Is it how we deploy larger mirrors, more mirrors, the complexity of it? Are we looking at focusing possibly on going back to visible light spectra? Are you looking at orbit and distance? Where do you see us in 2030, 2040, whenever that might get off the ground?
The biggest barrier is funding. But beyond that, I would say that really the power of a telescope is the size of its mirror. It's its light bucket. The bigger your telescope, the more light you can collect, the more sensitive you are. So the Habitable World Observatory, we're hoping for at least as big as Webb. There's some sort of more grandiose plans for something that's 12 meters. Again, funding is really the limiting factor to that. Or even trying to build it. Is this something that we need to launch in pieces and assemble in space, like the International Space Station, for example? But one thing that we are really hoping for with Hab Worlds is that it would simultaneously, sort of like your question, observe ultraviolet, visible, and infrared light. So it would combine those specialties together. It would become this sort of super Hubble, super Webb together. But really, something that we are doing in the next decade, because we have fewer constraints in terms of space, is building the next giant telescopes on Earth. So there's a 39-meter telescope being built in Chile. And that would really give us a huge light bucket, but of course, we'd be constrained to looking at visible light. A little bit of infrared, a little bit of the near infrared.
Awesome. We got time for, I'd say, 2 more questions. We'll have 1 more online, and we've got a question up front here, Annie, after.
Great, thank you. Next question is regarding the L2 Lagrange point and band and how that was found. Are there more such pockets of space like that that could be used for other telescopes? And how do we know that that was the best place to put it?
Yeah, so Lagrange points are fairly simple things that you calculate as a physics undergrad. It's not fun to calculate, but you can do it. Essentially, when you have different masses, 2 masses, for example, in this case, the Earth and the Sun, there are specific points in that gravitational system where the gravitational forces are in equilibrium. So it's relatively easy to stay in those spots. And there's 5 Lagrange points in total. And Lagrange 2 is interesting because it's a quasi-stable point. That means that sort of instead of imagining it as sort of a trough or a divot where you can easily fall into it, it's more like a saddle or the back of a Pringle. So you can stay there, but if someone knocks you off, you'll roll off. And so there's less accumulation of asteroids and micrometeorites, for example. So it is a very nice place to put telescopes because you don't need a lot of fuel to keep things there. There's not too much of an accumulation of debris, and it's always far behind the Earth, so it doesn't have to deal with infrared radiation or different kinds of radiation from the Earth or the Moon. But for example, solar telescopes are in the Lagrange point in front of the Earth, so they have more direct access to the sun.
In those ancient galaxies, is there a way of showing if they're more devoid of heavy elements since they're so old, there hasn't been enough supernovas and things to...
Yeah, absolutely. So using spectroscopy, we can get that chemical fingerprint. Yeah, and so one of the things that we're really looking for is what we call population 3 stars. Okay, astronomers are weird, like our brightness scale is inverse, like a negative is brighter than a positive. We did the same thing with populations of stars. The first population of star is called population 3, and then we count backwards. And so they would be the first stars ever born. So they will be very pristine. They will only have the light elements. They won't be contaminated by elements that are heavier, like iron, even elements that need a supernova explosion to happen. Well, it's harder to do planets when you don't have any of the heavy elements, certainly, but we wouldn't have the kind of resolution to look at planets in those early galaxies. But yeah, the metallicity of these different stars and galaxies tells us lots about how young they are. And we're looking for pristine things, which means they're very young.
I'm sure there's lots more questions, and maybe there will be an opportunity here after we end the formal events. But
absolutely.
Thank you, everyone, for your questions.
Thank you. Great. Thank you.
Good job. All right. It's just my job now to end our evening in here. Fantastic presentation, and really appreciate, Natalie, that you shared your research and your work and your passion with us tonight. This is our last EARTHx presentation for the season. EARTHx will return in the fall, but in the meantime, there are many more Faculty of Science events coming up, including some other exciting public lectures like this. So I encourage you to check the Faculty of Science website and follow our social media to see announcement details about these other events in the near future. At this point, I want to thank you all for joining us this evening, both online and in person. We hope to see you soon, and please drive home safely.